So now that we figured out how to build an adder, let's build a counter. And a counter is just an adder that counts up every time it gets a clock signal. So what we want is we want the next value of the counter to be the current value plus 1. Let's take a look at hooking this up. So first we connect the carries for our adder. So we've got our 2 carries going out. Then we're going to add 1 every time. So that means we're going to connect B to B1, so 0, 0, 1. So there we are, we've got 1 going in. And now A is our current value, so we're going to have the current value going to A, because we want to add 1 to get the next value. And that means the output, or the sum, is our next value. So this is the next value coming out of our adder. Now we want to hook those up, we hook the sum into the input, and there we are. Now we've hooked this up, our next value is going to become our current value, then we're going to add 1 to it and create a new next value. But there's a problem with this. The problem is we have this feedback loop. So the next value and the current value are the same wire. There's no way to separate them. There's no way to say wait until we get the clock signal to update the current value. So let's take a look at how we're going to break the feedback loop by adding state. So we have the same thing, we want next value to equal current value plus 1, but now we only want to update when we get a clock signal. So to keep these separate from each other, what we're going to do is add a latch. And what a latch does is it only moves the data from its inputs to its outputs when it gets a clock signal. So it's going to remember the previous value until the clock signal tells it to update. So here's our latch. Again, we have 3 latches because we have a 3-bit value, and now we're going to hook it up. So the most important signal to the latch is, of course, the clock. This is the signal that tells it when to update the state. And then we're going to put the next value from our adder going into our latch. So we wire that up, and then coming out of the latch is going to be the current value, and now this wraps around. So the latch is going to separate the current value and the next value and only update them when it gets the right clock signal. So now we're only updating current value to new value when the clock signal occurs, so we don't have a feedback loop. One way to think about the latch is sort of divided in 2 parts. And what the latch does is when it gets a clock signal, it moves the input over to the output and it remembers it. So only when you get the clock signal are you going to update the current value from the next value. So let's take a look at what happens on the clock signal. Here's our latch, and here's a table describing what's going on. So this table has the clock going from 0, 1, 0, 1, 0, 1. It has our current value, the 3 bits of our current value, and the 3 bits of our next value. So this next value is coming directly out from the adder, and this current value is coming directly out from the latches. And what we'll see is that when the clock goes from 0 to 1, the latch is going to move the data across and the counter will function. So let's walk through this in time. So in the first time step, our current value is 0 and our next value is 1. Because the current value is going right into the adder, we're adding 1 and we get 1 for our next value. Now, when the clock goes from 0 to 1, what happens is the latch transfers the next value to the current value, and now the current value gets updated to 1. After the current value is updated, it immediately goes right through the adder and we calculate a new next value, but that new next value doesn't go to the current value because we have to wait for the clock to go from 0 to 1. So now the clock goes back to 0 and we stay on the current value we had. Next time the clock goes to 1, the latch is going to take its new next value input and move it to the latch's output, which is the current value, and will update the current value to binary 2. When the output of the current value is 2, it'll go right into the adder and will immediately calculate the new next value, but we don't update the value of the current value because the latch only updates when the clock goes from 0 to 1. So the next time it goes from 0 to 1, we're going to move the new next value out to the current value, the latch will store it in there, and we'll go on and calculate the new next value after that. So what we see here is the latch is updating only when the clock goes from 0 to 1, but the adder updates as soon as its input changes. And this is because the adder is combinational logic and the latch is a state element. Here's another way to look at the same thing. Here we have the clock, the current value, and the next value. And what we see is when the clock goes from 0 to 1 in time, we see the next value moves over to the current value, and then we immediately calculate the new next value. But we don't update the current value until the next time the clock goes from 0 to 1, and then we calculate the new next value, and so on. So when the clock edge rises from 0 to 1, The next value is stored as the new current value, and the new current value goes through the adder to figure out the new next value. And everything here takes some time. So take a look at this. Here's where the clock went up from 0 to 1, and here's where we finally calculate our new next value. So here's a question. What limits how fast we can run the clock? Well, what limits how fast we can run the clock is how long it takes from when the clock goes up until we've calculated the next value. Because we can't have the clock go up again until we're done with this calculation. So the clock speed is limited by how fast we can get through this combinational logic. So, what's the big picture of sequential logic? We use state elements to store the current state, and we use combinational logic to calculate the next state from the current state. So here's our combinational logic that's going to calculate the next state, and it uses the current state and generates the next state. We made a feedback loop such that on every clock signal, we go and we update the new current state from the next state. But it's only on the clock signals that we update it. Remember how this state memory works. When we get the clock signal, we take the new input value and we store it to be the new output value. Of course, for this to be useful in general, we need to have inputs and outputs. So for our counter, the outputs were what we were counting, and the input should have been something like start or reset. And the clock speed is determined by how quickly the next state logic can update. So if the next state logic is very complicated, it may have to run slowly so that it can update before the next clock signal. So to summarize state elements, they store state, their memories, and they only update at specific times. For example, when clock goes from 0 to 1. We use combinational logic, these are gates, to calculate the next value, and state elements to store the current value. We do the update, which is where we update the current value to the next value on the clock signal.